In today's episode of Trigonometry, we're going to do some very exciting equivalent trig expressions. You've done a couple of these already, but we're going to do a few more new ones this year. A couple of them you actually have kind of seen, and you probably noticed even on your own, but didn't make the connection. So we're going to go through that today and just take a quick look. Okay, the first two identities that I want to look at, and I put down here that these are from grade 10 or somewhere. You may not have seen these before. It's possible that your teacher skipped over them, but we'll cover them now, so that's okay. And a trig identity is just a mathematical statement that is true regardless of the input that you put in here. So what this is saying is that no matter what angle you plug in for theta, tan theta will be equal to sine theta over cos theta. And similarly, sine theta squared plus cos theta squared will always equal 1. Doesn't matter what angle you plug in. It can be a negative, a fraction, whatever. These will always be true. I'm going to just really quickly go over why they're true, but the biggest part is that you're able to use them. Now the tan one, I'm actually going to try it and justify it by going backwards. Oops. Stop jumping. Okay, so I'm going to start off with sine theta over cos theta. Well, if you recall from our ever so popular SOHCAHTOA, by definition, sine theta is opposite over hypotenuse, and cos theta is adjacent over hypotenuse. Now, if I multiply top and bottom by hypotenuse, which is legitimate, those cancel, and I'm left with opposite over adjacent, and that is by definition what tan of theta is. So there's proof that tan theta equals sine theta over cos theta, meaning if you have a tan theta, you could replace it with sine theta over cos theta, or if you have a sine theta over cos theta, you can replace it with tan theta. They are exact equivalent expressions. How about the other identity? Sine theta squared plus cos theta squared. We're going to talk about this more, but you probably recall that you could have written this as sine squared theta plus cos squared theta equals 1. When you put the 2 or the exponent on the sine, which is a little different than putting it on the theta, it's the equivalent of squaring the sine theta as a whole. It's a weird notation, but that's the way it works out. I wrote it in a way that hopefully will be more precisely obvious what it is that I'm getting at. Now this one here, if we do kind of the same trick, sine theta is by definition opposite over hypotenuse. Cos theta is adjacent over hypotenuse. Oops, I shouldn't use an equal sign because I'm trying to prove they're equal, not... There we go. That's equal to opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. But if you recall, for a triangle, a right-angled triangle, we have opposite, adjacent, hypotenuse. There was a formula that looked like this: a squared plus b squared equals c squared, or in our case we could call that opposite squared plus adjacent squared plus, equals hypotenuse squared. So since opposite squared plus adjacent squared are hypotenuse squared, that's hypotenuse squared over hypotenuse squared, which is equal to 1. So despite the fact that it may not look like it, this is really just a trig version of the Pythagorean theorem. So now we have two beautiful identities that we can start along solving all kinds of interesting trig identity problems. Now, the next thing we're going to take a look at is relationship between an angle and pi over 2 minus an angle. And just as a little reminder, we're going to be using the pi over 2, but that's the same thing as saying 180 degrees. Sorry, not 180. Pi over 2 is 90 degrees. Get out of my way. 90 degrees minus theta. Now this part we're going to do in radians because, well, that's the way the book does this one, and I try to stay with the book since that's the questions you're going to be answering afterwards. But let's take a look at this diagram here. So here we have a diagram. Our angle down here is theta. We know this is a right angle over here, which is pi over 2. So this angle is going to be pi over 2, or 90 minus theta, since these two angles have to add to 90. What am I doing? Oh, okay, there we go. Add to 90 degrees, or pi over 2. Same difference. Okay, so now if we use the variables that are on the diagrams, the a, b's, and c's, at least the lowercase a, b's, and c's, which are the side legs, the sine of theta is going to be opposite over hypotenuse, which is b over c. The cos of theta is going to be adjacent over hypotenuse, which is a over c. And the tan is going to be opposite over adjacent, which is b over a. Not too tricky. Now we're going to do the same thing, but we're going to do the angle up here. And we're going to see what happens. If we do this angle up here, its opposite is a, so opposite over adjacent is a over c. Adjacent over hypotenuse. I think I'm screwing all these up in my words here. I'm biting my own tongue today. Sine is opposite over hypotenuse, a over c. Cos is adjacent over hypotenuse, b over c. And tangent is opposite over adjacent, a over b. Okay, so all I've done is look at my diagram and write down what they are in terms of a, b's, and c's. But now from that, I want to actually draw the conclusion that the sine of pi over 2 minus an angle, that's a over c. Well, that's the same as cos theta. So that's actually one of our identities. And similarly, if we take a look at cos pi over 2, b over c, that's the exact same thing as sine theta. And our final one, purple, it's purple. Tangent of pi over 2 minus theta is a over b, which is similar to this one, but not exactly the same. One's a over b and one's b over a. So I can say that this is 1 over tan theta. And I'll put down here that that is actually cotangent theta. I personally am completely cool with using all the primary trig ratios and just the primary trig ratios, but I do want to point out that it is actually equal to the cotangent. Okay, that's kind of cool. Well, what about if we want to look at the relationship between x and pi over 2 plus theta? That brings us to this diagram here. I'm going to give you about 5 seconds to look at that diagram before you start bleeding out your ears, because it is confusing. But I'm going to try and justify it, and I actually made a bigger version down here that we can look at a little closer. This is the same diagram. I just want to focus on the diagram without actually worrying about what we're doing with it, and we'll do that later. Okay, so we have angle theta measured there. I'm going to focus on this right-angled triangle. Actually, you know what? Let me just do that in red. Ooh, that was not what I wanted. Theta. This triangle in red. Okay. And if that down there is theta, then this angle up here is pi over 2 minus theta. Okay. That, because of Z pattern and for several other reasons, if you remember your stuff from grade 9 and 10, makes this pi over 2 minus theta. That makes this theta, since this is just a 90-degree rotation. This is basically saying take theta, push it another 90 degrees until you get up here. So this is theta, and this up here is pi over 2, or 90 degrees plus theta. If that's theta, this is theta. That makes this pi over 2 minus theta, and this pi over 2 minus theta. And now what I think you'll see is that the original red triangle is exactly the same as this triangle. Which means if the original variables that are on here, A, B, and R standing for radius, by the way, this would be R. And the A and B have reversed spots. So this is A over here, and that's B there. Okay, so that's what that diagram is showing, is that if I add pi over 2 to an angle, I get the same radius, and I reverse the A's and the B's. So going back here, if I take a look at sine theta in my diagram keeps bumping every time I touch it. Sine of theta is equal to opposite over hypotenuse, or B over R. Cos of theta is equal to A over R, and tan of theta is equal to B over A. Okay, going up to here, pi over 2 plus theta, I'm going to focus on this triangle. And I realize that this is not technically theta, but we're gonna pretend it's like the related acute angle thing. This is the R, this is the A, and that's the B, which we just figured out in our lower diagram, lower version of this. Okay, so the sine of this triangle, looking at this angle, because for related acute angles, we always look at the central angle. We don't look at anything else. So that's going to be opposite over hypotenuse, which is A over R. Cos is adjacent over hypotenuse, B over R. And tan is opposite over adjacent, which is A over B. However, looking back at yesterday's lesson, there is actually one other little detail we need to take into account, and that's that we're changing quadrants. So we have to apply our cast rule. And our cast rule says only the sine ratio will be the same. The cos ratio will have the opposite sign, and the tan ratio will have the opposite sign. So they're all positive in the first quadrant, which is where theta is. Only sine is positive in the second quadrant, which is where pi over 2 plus theta will always be. If you take an angle between 0 and 90 degrees and you add 90 to it, you're always going to end up in the second quadrant. Okay, from that, we can conclude that sine pi over 2 plus theta, A over R, must equal cos theta. Secondly, we can conclude that cos pi over 2 plus theta, negative B over R, is going to be negative of sine theta, since sine theta is B over R. and tan theta, negative a over b, tan pi over 2 plus theta is negative a over b. Tan theta, I'm not underlining that because I'm not trying to show that they're exactly equal to, the inverses of each other. So I can say that that must be negative 1 over tan theta, or negative cotangent theta, if you're someone who likes the secondary ratios. Okay, so that seemed painful, but I think it actually wasn't as bad as it looked. This is a hard diagram, like I said, to wrap your head around and to go back and look at, but I think if you follow through, you'll see that using the variables a, b, and r, you can show all these trig identities to be true. And if you don't believe that they're true, you can always go and graph them in Desmos. And why don't we, just for the heck of it, no, actually, let's not. Let's save that for another lesson. We shall graph later. All right. Now let's see if we can use this to solve some interesting little problems. Number 1, given that sine pi over 5 is equal to 0.5878, it doesn't tell us a lot of detail except that pi over 5, which is not one of our special angles that we know anything about. Find each of the following without a calculator. Interesting. Okay, so here's what we're going to do. I'm going to look at this and think 3 pi over 10. I'm just going to kind of do a little aside here. 3 pi over 10 is that equal to 2 pi, or sorry, pi over 2. The only ones we know so far are pi over 2 plus an angle or pi over 2 minus an angle. So is that pi over 2 plus something? Well, no, because it's actually smaller than pi over 2. So I'm going to suggest that it's pi over 2 minus something. So specifically, it's 5 pi over 10. That's pi over 2 converted to a common denominator of 10. I know I need to have 10 on the bottom, minus 2 pi over 10. Okay, so at this point I realize it may be a little tricky to figure out how I figured that out, and honestly in my head it was a little bit of trial and error. But do we agree that it's true, that 3 pi over 10 equals 5 pi over 10 minus 2 pi over 10? And hopefully you do believe that that is true. And I can put those two fractions into lowest terms, and that is pi over 2 minus pi over 5. So what does that mean? That means that cos 3 pi over 10, if I go back up here, way up here, cos pi over 2 minus theta equals sine theta. Cos pi over 2 minus theta is equal to sine theta. So cos theta, or cos 3 pi over 10, is equal to cos pi over 2 minus pi over 5. Well, that's pi over 2 minus theta, and that's equal to sine theta. And lo and behold, we're told in the question that that's equal to 0.5878. So there we managed to do it. I never picked up a calculator, and even if I had, I don't think it would have helped me any. For cos 7 pi over 10, for part B, let's try a similar trick. I'm going to note that 7 pi over 10 is equal to 5 pi over 10 plus 2 pi over 10. And again, after you've seen a couple of these, I think you'll start to catch on to the patterns. Basically, we want to deal with a pi over 2 plus or minus something. Because this is bigger than pi over 2, it's going to be a plus. And pi over 2 as an equivalent fraction with a base of 10, or a denominator of 10, is 5 pi over 2. Okay, so that's pi over 2 plus pi over 5. So cos 7 pi over 10 is the same thing as cos pi over 2 plus pi over 5. And if we go back up just a little bit, pi over 2 plus theta equals negative sine theta. Cos pi over 2 plus theta equals negative sine theta. In this case, our theta just happens to be pi over 5. And that's just the negative of what we're given at the top there, so that's negative 0.5878. Some of you are probably asking, where will I use this in real life? And the answer is, I have yet to see it. Trig identity stuff, for the most part, I won't say it's completely useless. It comes in some really handy things in computer programming and physics. But for the most part, this is just training your brain to recognize patterns and try to be able to manipulate those patterns to your advantage, which is actually a huge mathematical exercise. So think about like working out to prepare for a big sports game. This is the equivalent of the big workout. This is the pumping your muscles and taking steroids. Don't do that, by the way. That's bad for you. I'll explain the physics behind why taking steroids is bad if you ever ask me. Anyway, that is another story. All right, let's see if we can do something similar down here with question 2, which unfortunately uses some of those inverse or reciprocal trig identities, which I absolutely hate, but we can still work with them. Okay, to start this question, we're going to take a look at the angles we're working with. So we're given cosecant 2 pi over 7 equals 1.2790, and we want to figure out what the secant of 3 pi over 14 is without a calculator. Now, without even worrying about the cosecant, the secant parts, let's just look at the angle. 3 pi over 14. Now, I know based on what I've got so far that this is going to have to be pi over 2 plus something, plus an angle, or pi over 2 minus an angle. Well, 7 pi over 14 is a pi over 2, so this is obviously pi over 2 minus something. So just at the side here, let's play with this just a little wee bit and see if we can figure it out. 3 pi over 14 has to equal pi over 2, which is actually 7 pi over 14, minus, well, 3 is equal to 7 minus 4. 4 pi over 14. So I can replace 3 pi over 14 with pi over 2 minus 2 pi over 7 when I put that into lowest terms. And I think we're on the right track here because sure enough, we're given the cosecant of 2 pi over 7. So now what I'm going to do is I'm going to say secant. And just as a reminder, secant is the inverse of cosine, and cosecant is the inverse of sine, just to remind you. We'll worry about that in just a second. Okay, so secant 3 pi over 14 is the same thing as secant pi over 2 minus 2 pi over 7. That's the equivalent of 1 over cos pi over 2 minus 2 pi over 7. And now we look back to our trig identities of cos pi over 2 minus, cos pi over 2 minus theta. All the way back here. Cos pi over 2 minus theta is equal to the sine of theta. By the way, you can pull out, there's a trig identity sheet that I'll post, and you can take a look at it to refer to for all these, because I'll be honest, I don't remember them off the top of my head. I can derive almost all of them from scratch, but to use them, you want them a little faster than that. So that's going to be equal to 1 over sine 2 pi over 7. But 1 over sine is cosecant. And I think I know the value of cosecant 2 pi over 7 because I'm given it right there. All right, that was kind of fun, actually. I know what you're all thinking. Mr. Ray has a very sick sense of what is fun. And you're correct. I like math. Okay, so just to remind you, there are some homework questions there. I put down only do the primary trig ratios if you want. But for the most part, I do want to remind you that all of the secondary ratios have equivalent identity expressions, which we kind of just used. But you can get them all by converting to primary and then converting back again at the end. And it's up to you whether you want to do it that way. If you like working with the primary trig ratios like I do, then by all means do that. If you're comfortable with the reciprocal ratios, then, or the secondary ratios, by all means use those. Either way, give those homework questions a shot. Let me know if you've got any problems. And otherwise, I will see you in the next lesson. Have a fantastic day. I'll see you later.